Hi, Weichi.
You're muted, Weichi.
Well, hello, everyone, and I'd like to welcome everyone to the May 2020 meeting of the St. Louis Java Users Group, and I'm glad you could make it to our little online version. Just for people who haven't been before, attendance is free. We don't have a formal membership list. We normally meet on the second Thursday of every month except December when there is no meeting. And normally we start at 6 p.m. with food and social, and we have food sponsors that provide food for us, but the actual presentation generally starts at about 6:30. When we're meeting in person, our current meeting location is the OCI training room, and they're at 12140 Woodcrest Executive Drive, Suite 310. Upstairs in St. Louis, and so who knows, there may be people here from way outside St. Louis watching, and that's just fantastic if you can join us. We welcome you. So I'd like to introduce some of the members on the steering committee. From left to right, we have Ted Doyle and Todd Zimmerman, me, I'm in the center there. Then we have Weichi and Kathy. And so if you'd like to reach us on the steering committee, we have an email address. If you just send it to the address shown on the screen, javasigsc@ociweb.com, it will go to all of us on the steering committee. I'd like to thank our sponsors. Without the support of our sponsors, the St. Louis Java Users Group would simply not be possible. I'd like to thank OCI for providing the meeting location, and they also sponsor our web hosting for our website. You can find us on Google search. There's an OCI website that tells more about the group, and it has slides going back all the way to 1997. We've been around for a long time. I'd like to thank Edward Jones for sponsoring our meetup fees. It's free for you to come and attend a meeting on Meetup, but we have to pay a subscription on our end to keep the site going. I'd like to thank two recruiters, Signature Consultants and Adaptive Solutions Group, and they often will supply the food for our meeting when we meet in person. And so if you are looking for a Java position, I would definitely reach out to one or both. We are also sponsored by JetBrains. They sponsor licenses that we raffle at each of our in-person meetings. We're having to hold on to those right now because we can't hand out the info very well, but as soon as we're back online, we'll be raffling those again. We have Elastic, which sponsors, they're the people behind Elasticsearch, in case you don't know. They sponsor some gift cards that we raffle at the end of the meeting, as well as Intertech, and they sponsor the famous screaming flying monkeys. You throw them against the wall and they scream. But in real life, what they do is they are a technical training company. So if you're looking to do like a lot of online education to improve your technical skills, you might want to pay a visit to the Intertech website. Manning has been sponsoring ebooks for quite a while, and we've been raffling those. We'll get back to that again. And along with Pearson, they've been sponsoring physical books along, for us as far as raffling. If you are interested in becoming a sponsor, you can contact us at that email address that I showed earlier, javasigsc@ociweb.com. We're always looking for more sponsors to keep the group successful. Now here's our upcoming presentation schedule as it stands today. Now a lot of these were scheduled before the coronavirus hit, but we have scheduled right now for June 11th, developing low latency applications with Hazelcast. On June 9th, migrating beyond Java 8. August 13 will be Architecture Foundations, and October 8th is This Ain't Your Parents' Java. And so we've got some big name speakers. A lot of people probably know Venkat. He's been here before. And Neil Ford is also pretty well known. Dahlia works at IBM, and Sharath at Hazelcast. Now, we don't know exactly when we'll be able to start meeting in person again. So if you want to know whether this is going to be online or in person, my best advice to you is to just watch Meetup. Watch Meetup at that URL for updates to our presentation schedule and location, and we will post that as soon as we have information as far as when we'll be meeting online or if we're going to go back to meeting in person, subject to whatever restrictions might be in place. And as always, if you have any questions, you can always email us if you'd like to give a presentation or be a sponsor for the Jug. So once again, thank you for everybody coming here tonight. Tonight's presentation is Why Clojure by Alex Miller. And I believe, among other things, he's a sponsor of the Strange Loop conference, but I don't know what the status is of that is either. You might want to fill us in if there's anything happening there. So Alex, why don't you take it away? And then I'm going to eventually try to turn off my camera and mute my microphone so you can have the floor here.
All right, thanks, Bruce. I'll take over my screen here. Let me know if you can see that. Look good?
Yeah, that looks good, Alex.
Okay, and I'm going to sort of forcibly mute everybody and then unmute myself. All right, hopefully everybody can still hear me. And I will try to pop up a chat window here just in case I see anything. So I will have a couple breaks where I will try to look at the chat room and get to any questions. So if you have questions along the way, feel free to just drop them in the chat, and I will pick them up when I stop a few times during the middle. So as Bruce said, I'm Alex Miller. I've lived in St. Louis most of my life. I've started several user groups here, spoken many of them. And then, as Bruce mentioned, I'm the founder of the Strange Loop Conference in St. Louis. And unfortunately, we've announced that we're canceling our in-person conference for this year. I am actively working on doing some kind of an online version of Strange Loop for this year, but still TBD exactly what that will look like and exactly what it will be, but working on that right now. So as far as Clojure goes, I've been using Clojure for about 10 years, and I have been at Cognitect for about 7 years. Cognitect is where the creator of Clojure, Rich Hickey, works, and at this point, Cognitect is a fully Clojure oriented consultancy, and then we also have a product team that makes a database called Datomic, which is written in Clojure, and it's a sort of cloud-native, fact-based database, and has lots of very interesting, cool features to it. It's a great database. If you're in the market, feel free to look it up. And big thanks to Cognitect for them. We're borrowing their GoToMeeting for this, and for supporting me. I actually work on Clojure itself full time. So I'm just paid by Cognitect to work on Clojure. So living the dream of full open source, full-time open source development. So I wanted to start this off, the little block here at the, and I'm going to do this entire thing in the editor. So thanks to IntelliJ or to JetBrains for sponsoring it. I use IntelliJ. This is IntelliJ. I'm using a Clojure plugin called Cursive, and I'm actually just using the community version of IntelliJ and a paid license version of Cursive, although there are also community versions of that. So I wanted to start with kind of lead with the most important thing, and that is I worked in Java. I've worked in Java since 1997. So I have a long history of being on the Java platform, way back to Java 1.0.2, I think was when I first started working on it. And I worked in it for a long time, wrote hundreds of thousands of lines of code, still use it because Clojure is written in Java. So I still use it on a regular basis, but it does have some problems. And at some point, I found those problems to be pretty irritating and to be getting in the way of me to actually do really useful development. And through another story, I found Clojure. And so I wanted to highlight some of the things that I think are issues that I've seen in Java and why those things are, for me, solved in Clojure. In general, there's a cluster of problems around mutable Java objects, custom equality protocols, locking to modify mutable fields, and all that kind of stuff that is at the heart of Java and is, in my mind, at the root of a lot of problems, a lot of bugs and concurrency issues that I ran into when I was using Java. In Clojure, all of the values, including collections, are immutable. That rules out a whole class of problems, but just by itself. And it is just a simpler model to deal with. After you've been using Clojure for a while, you can kind of look back at Java and see that every class that you make in Java is really its own brand new interface. Every time you write, public class and start making methods in there, you're creating a new interface, usually an interface wrapped around data that's brand new, and you have to teach people how to use that interface. So in Clojure, we instead have data literals, and we have generic data interfaces around those data literals, and we don't create things like classes generally. And that's just a more generic way to program, something I prefer. There's kind of a conflation of identity and state in object-oriented programming, and where an object is an identity, and it also has state inside of it. And those two things are kind of put together in Java. Whereas in Clojure, they're really separate. So you really have values, immutable values, and then you explicitly create a state container and give it an identity, but it's separate from the actual value part of it. And Clojure also has a software transactional memory system that you can use to do coordinated changes in state, if you like. I did a lot of work in sort of pushing Java code as far as I could go with it, and I found that I struggled with running into limits to abstraction. I'm sure most people are familiar with design patterns, Gang of Four, and all that stuff. The main problem that I've come to think about it as in Java is that Java does have lots of tools for abstraction, and interfaces are really probably the key one of all those. The issue with interfaces in Java is that typically when you make code more abstract, that means pulling interfaces out and making things implement those interfaces. And that means that to make the code more abstract, you also are adding code. And so if you were really pushing abstraction, you tend to be continually making your code bigger. And it is more abstract, but it's also larger, which makes it harder to deal with at some point. Whereas in Clojure, I feel like a lot of the methods of abstraction are really things that allow you to make your code smaller. And that's a little counterintuitive, but it kind of goes to this generic interface kind of idea that is prevalent throughout Clojure. And that means that as time goes on, your code doesn't necessarily get larger. It can get more abstract and more reusable without increasing in size. And there's a lot of tools for that. Functions are generally a big hook that you can use for most design patterns. And then macros are a way to abstract syntax. And so that's a pretty powerful hook. Java tends to have a pretty inflexible polymorphism model. It's really based around class hierarchy and absolute class hierarchy, single inheritance and interfaces. And one of the big problems is that that's baked into Java. When you write a class, the things that it implements are baked into it at the point where you write it. And if you want to add a new kind of interface in, you have to go back and change the class to do that. Clojure's polymorphic features, which are called multi-methods and protocols, allow you to basically add new cases without changing your existing code. And so that's a pretty powerful tool to let you define an abstraction and continue refining it after that point without having to go back and change the code that you already have. Just in general, Java, when you're working with Java, because it's a compiled language, it has some level of verbosity, and then you have to go through the compile cycle and run your test suite and do all that kind of stuff. Whereas with Clojure, you're really doing REPL-based development, which is very interactive. And because I really wanted you to feel that, I'm going to do this whole talk in the REPL interactively, while we're talking through it. And it's really, this is exactly the tool and exactly how I work with Clojure code every day. So I thought it was really important to give you that sort of feel to things. And then finally, this is something that I think takes a long time and a lot of programming experience to start to see, but I find Java has a certain level of brittleness. If you've ever had the case where you have to go into your web app and change some fields, and then you have to change some fields in your request object, and then change some field in your the top of your web stack as it pulls data in, and then you change some fields in your ORM, and then you change some fields in your database, and all those things have to be in sync to actually add a new feature. That's the sort of thing that Clojure is really designed around this growth not breakage model, and working with open maps, open extensibility, and trying to minimize those kinds of things, so that changing your requirements is something that all software does over time, and Clojure is really designed to sort of grow with your code as it changes. So, or grow with your requirements as they change. So, so right now, if that was all good for you, you can just stop watching. Those are the highlights. But we'll talk through a lot of examples, and I'm not going to try to teach you all Clojure, but I am going to try to teach you a little bit of the core of it so that you can get a feel for it. So there are really a handful of core data types in Clojure. This is not an exhaustive list, but this really covers the bulk of the simple values that you'll encounter in Clojure. So I have a keystroke that I can hit to either evaluate, to evaluate an expression. And what you'll see is that over here on the right is, this is an output pane on top and an input pane on bottom. And if I write something in there, you'll see that the input gets echoed, and then I've got output. So this is an interactive REPL over here that I can type into. But that's not how most Clojurists work. So most Clojurists work with a REPL connected editor. And so what that means is I'm going to pick up some expression in my editor where my cursor is, and I'm going to send that to the editor. So you saw the exact same thing just happen. I just did it from the editor instead of doing it from over here in this input pane. And that's, like I said, this is exactly how I work every day. This is how every professional Clojurist that I know works. It's just the way to fly. So we've got integers, which are actually Java lang longs. We've got floating points, which are actually Java lang doubles. We have ratios, so that's kind of cool. Java doesn't have those, but that's kind of nice. We've got strings. Strings are actually Java lang strings, so they're the exact same things. This is a syntax for a single character. So again, it's a Java lang character. None of these are wrapped in any way. These are just the same types you have, exactly the same things you have in Java. This is a keyword, and keywords are a little bit different. We'll talk about them more later on, but a keyword is essentially an enumerated value. So any place in Java where you would use a public static final string or something like that to hold some kind of a enumerated value, that's something where Clojure would use a keyword. And keywords just evaluate to themselves. They're actually interned like strings are in Java. So you can use 100 of them, and you're actually only using one instance of memory. And because of that, that means that their equality check is really an identity check and is very fast. You got true and false. These are just exactly Java Boolean trues and falses, and then nil, which is just Java null. So we have many of those are, like I said, are Java types. And then we have ways to combine those values. And this is not all of them, but it's the subset that you'll see the vast majority of the time. And these are vectors. Vectors are, all of these collections are heterogeneous, all of them nest. So you can nest vectors inside maps and maps inside vectors and all that. That's all fine. The types are unimportant. They're all basically, in Java, they'd be equivalent of object, as like raw collections or whatever. Commas are white space. Literally, you can just put as many as you want in there. It's totally fine. They are literally treated by the parser as white space. Sometimes the Clojure will print commas where it happens to make things more readable, but they're never required in literally white space. So Clojure is a Lisp. Lisp stands for list processing. So of course we have lists. Lists just look like this with the normal curly parentheses. I'll talk about the quote in the beginning of that line later on. We have sets. Sets, you'll notice that when this got printed out, it did not get printed in the same order, and that's because sets are unordered, and they basically print in some arbitrary order. You should not rely on that order. It's actually based on the hash value of the elements. Sets can't have duplicates, so if you actually try to create a set with two of the same thing, it will actually literally refuse to read it. If you actually take that set and then try to append a value that's already in it, it will just not do anything, basically. You'll get back the same set. And then we have maps. So maps are alternating key value pairs. So A is a key pointing to 1, B is a key pointing to 2. You notice that the printer printed a comma there between the pairs just for usefulness. Sometimes you'll see in actual code, you'll see a Clojure programmer put a comma in there just for clarity, but it's not required. All right, so this is a good point to talk for questions. I don't see anything in the chat, so I'm assuming that I have perfectly explained everything so far. But if not, put something in the chat. I'm going to go on. So nothing gets interesting until we can start actually doing something, right? We want to actually invoke functions and write code, right? So you've probably have heard enough about. I request to make text a little bit larger here, so I can do that. I'm on a big monitor. I can do that. Hopefully that'll help a little bit. So we can evaluate +1, 1. So Clojure uses prefix notation, like all Lisps, and that means that the operation is at the beginning and then the arguments are after that. People enlarge the screen. I can enlarge it, but I don't know that it'll be any bigger for you. Let me bump up the font one more. Let's see if we can get a little bigger here. All right, hopefully that's a little better. All right, so a lot of people have the initial reaction of, oh my God, there's so many parentheses. That's a common list for Clojure reaction. There's not any more parentheses here than there is in your Java code. Every time you invoke a method in Java, you use parentheses too. So, so get over your whining. The same number of parentheses here. They just happen to be at the beginning. That's the only difference. And there's no semicolon, so other than comments here. So, I think we're actually winning on that score. But the big difference, of course, is that the operation is first. So here I obviously did +1, which gives back 2. I can look at something like a set and call count on it. There's lots of collection functions. I'm not going to go through all those. We might want to take a collection and add a new element to it. And the canonical operation for that in Clojure is conj. Conj is short for conjoin. It's sort of a universal append function, which works with all of the different collections. And you'll notice that I get back a new vector. Vectors are kind of like Arraylist. They're indexed and retain their order, all those kinds of things. And they can grow without bound. So we got all that stuff back, but this original thing here is an immutable value. So nothing happened to the original value that you passed it. It's not like calling .add on an array list or something like that. That's actually, which would actually modify the thing you passed in. Instead, you get a new instance. There's a question in the chat about whether that append copies the collection. The answer is mostly no. So the big trick here is something called structural sharing, which allows the new instance of the collection to share basically all of the parts of the old collection that it can. So this works with all of the different Clojure collections. And the big reason for that is performance. So working with Clojure collections is slower than Java collection, mutable Java collections, but not much. And in general, you won't notice. And it also makes all of your code immediately thread safe. So there are huge benefits to be had, and I would not trade it up in a heartbeat. If you really need to use mutable collections, there are several different ways to use that as well. And for high performance situations, you might want to do that. Contains is an option that will check whether, a function that will check whether a key is present in a keyed collection, in this case a map. So we ask whether :A, the keyword, is a key in the map. Let me get back to true there. So we've just been doing single individual expressions here. But now it would be more useful if we actually could keep some of those things around. So vars are a way to create globally named things. So def creates a var named x and gives it the value 5. So once I do that, I can reuse that. That becomes a name that's now sort of globally known. It's actually available. There's a whole namespace system. I'm not going to talk in detail about any of that stuff, but it's actually globally available by its fully qualified name. You could also just embed that in other expressions. Everything's fine. There's a syntax, so I'm going to introduce another special form here, which is called fn. Fn defines a function. So fn takes a list of arguments. Here we just got 1, which is x, and then evaluates some body of expressions. And I've only got one expression here, but there could potentially be more than one. In this case, it's just x plus 2. So that's sufficient to make a function, but that doesn't actually do much on its own, right? That's actually showing you a Java object. It's actually the class name, hash code, and toString of some object. So not too useful by itself. We could, if we wanted to, call this plus 2. We could, if we wanted to, just put this in a var, and then we could invoke it at that point. So that would work just fine. But the way that we usually do it is actually by using something called defn. And defn is kind of a contraction of def and fn. It's kind of combining what I just did here together into creating a var that happens to reference a function. And it has a few extra features in it as well. Things like the ability to specify a docstring and some other pre and post conditions and other things like that. So this defines a capitalized function. Got a docstring, it takes the string s, and then outputs the first string, the first character of the string, uppercased, and you're actually seeing an invocation of a Java static method here, and then combines that with a substring of s starting at 1 and going to the end of the string. So If we create that, we now have a capitalized function we can call. Worked perfectly. My vast test suite. Oh wait, I found a few other errors out there. Didn't really think about what happened if there was less than one character. So we might want to go back and fix this. You can fix this by putting a condition in here and say, if the count of the string is positive, then we do what we have. And if not, then maybe just return S, whatever you pass me. I'll just do that. So I just did a couple things there real quick, but I want to step back and mention a few of those things that helped me out while I was doing it. You see that I'm getting parenthesis matching on here. It's something that most Clojure editors will do. Obviously, there are parentheses and things like that. The other more important thing is I actually had this originally, right? And I started typing an expression. You notice that I just typed a left parenthesis here. It actually inserted the right parenthesis for me. And then I typed if, and then I hit another keystroke, and this is actually a thing called Slurp is actually the name of the command. And that Slurp actually, I can kind of go back and forth on it. So you see that I'm actually editing the structure of the code with a command here. And actually, I went too far there. And so there are a handful of commands, and this is created in something called paredit, which comes out of Emacs and old-time Lisp programmers and things like that, but has been fully adopted by Clojure. There's another paradigm called parinfer that's really more based on tabbing and things like that. It's a little more Python-esque. Both of them work great. But the big thing is that once everything is an expression and everything is parenthesized, you can actually start thinking of your code not as characters, but as expressions that I'm going to manipulate. And so there's a handful of these commands like slurp and barf and splice and kill are the four big ones that allow you to basically manipulate your code at the structural level instead of at the character or text level. At this point, you've actually seen all of sort of the what I consider to be table stakes for a Clojure development environment, which is you need to have an editor connected REPL, and you need to have structural editing and some sort of parenthesis stuff to help you visually help you understand what's going on, and that's really sufficient to be really an efficient Clojure editor, and all the major Clojure editors have that. So I just broke all my code here, so I should probably fix all this. I said, what if positive, if the count of S is positive, and then otherwise I'm going to do this, right? So let's check that still works, which it does. That still works, that still works. All right, so we fixed it all up now. So I'm trying to give you a feeling of what it's like to actually work in Clojure. There's a question about whether VS Code can do that. I haven't used there's a good plugin for VS Code, which called Calva. It does a lot of stuff. I have not actually used it, but I'm pretty sure it does have paredit support and parinfer support. So I'll talk about evaluation a little bit. We've actually now seen all the main basic values. We've seen all the compound values, all the collections. You've actually seen function definition and function invocation. You've actually seen all the rules of evaluation, although you weren't aware of it. So you've actually learned all the important parts of Clojure at this point. You're not ready to get a job yet, but you actually have learned an awful lot without even being aware of it. So the big thing in Clojure is that the rule for evaluating expressions, and everything in Clojure is an expression, is that in general, everything evaluates to itself. So if I go look at 1 and evaluate just 1, it evaluates to itself. Or if I evaluate, let's see, let's grab some random string here. If I evaluate string, all those basic things that I had at the very beginning in that initial list, all those things evaluate to themselves. All the collections evaluate to themselves. There's really only 2 exceptions, and you've seen them already. The first one is that a symbol actually a symbol is a name. And so we haven't really been talking about these explicitly, but all these functions I've been using are all what we call symbols. And symbols name something else. And so when you evaluate them, they evaluate to the thing they name. They evaluate to a function object or something like that. And the other special rule is parenthesized expressions. So in this case, when you write a list, the evaluation model for this is evaluate each of the elements inside the list and then invoke the first one as if it was a function. So in this case, 1 is not a function. So if we try to do this, you'll see that it says that's a syntax error. You can't cast long to an ifon. An ifon is the Clojure interface for things that are invocable. So it's important to understand, though, there's actually 2 steps happening here that are kind of, when I say evaluate, there's actually 2 different things happening that we can split apart. And so the first part is I need to read a string, in this case, the string, which is this string I have highlighted. Those are characters in this file. So read some string and output a Clojure data structure. And the Clojure data structure it outputs is a list with the elements 1, 2, the numbers 1, 2, and 3. And that's the job of the Clojure reader. And then the second step is, now that I have a Clojure data structure, evaluate that data structure. And what actually happens at that point is Clojure literally compiles that expression into bytecode and loads it in a class loader and invokes it. So I've been making all sorts of classes here as we do stuff. It's all behind the scenes, and you don't really know anything about it. It doesn't get written to disk. It's just happening in memory. So what's happening here is we're reading this into a list, which is good. Maybe that might be what we wanted in this case, but then we're evaluating that thing. So we need some way to read but not evaluate, and that's what quote is. Quote is just a little piece of syntax that says, read the expression immediately following it, but don't evaluate it. Just give me back the thing you read. And that is actually just syntax sugar for a special form called quote. And that is exactly, so these 2 things are exactly the same. And actually the reader literally rewrites this as quote 1, 2, 3. So at this point, we've actually seen a lot of the special forms in Clojure. Clojure is a dialect of, or not a dialect. Clojure comes from the Lisp tradition, I would say. So Lisp, as created by McCarthy back in the 60s, famously had 5 to 7 special forms, and that was all you needed to define. And at that point, you basically had bootstrapped the language. But that set of sort of axioms, you had enough to define everything else you needed in the language. Clojure is a more complicated Lisp than the original Lisp. It has somewhere around 20 special forms. But really, there's a lot of those are pretty rarely used. And so I've made a list here of the ones that are actually the most common special forms that you really need to care about. We've seen def, that's for creating vars. We've seen fun, that's for creating functions. We've seen quote, that's for read without evaluate. We've seen if, which is obviously an if. We haven't seen these yet, but do lets you basically evaluate a block of expressions as if it was a single expression. So it's just a grouping mechanism. Let is a means of creating local names, lexically scoped local names, which we'll look at next. Loop recur allows you to do a tail recursive loop, which we're not going to talk about at all. And then try, you might guess, is actually very similar to a Java try block. It allows you to evaluate a body of expressions and then catch an exception if one is thrown. And it also has a finally clause in it as well. Throw is used to throw a Java exception. And then dot is the sort of universal Java interop operator. So it allows you to get access to static fields, instance fields, invoke static methods, and invoke instance methods. And then there's some other special syntax that's built on top of dot, which actually use more commonly. And I guess I missed, there's some syntax for constructing objects, which I didn't really talk about. So one thing to see here is that maybe to compare with Java here is to say, if you have an if expression, it has break that out a little bit. It's got a condition, a then, and an else. So this is very similar to what you'd see in any language for an if expression. It is an expression, so it's more like a Java ternary if, with the I don't know which something like the thing with the question mark and the colon, the ternary if expression in Java. But it will return either basically the result of the then or the result of the else. And so we can evaluate that. And you'll see this is just finding a random number and seeing if it's low or high. So you'll see that I'm getting low, high out of that. Collapse all that back up a little bit. And then we talked about vars, which lets you give names to global things. Let is used to give local names to something. So within the lexical scope of this let expression, we can create some new names that are just valid inside this block. And if you nest lets, then you can see ones from the parent. You can also shadow ones from the parent if you want. That's fine. So here we're saying let A equals 1, let B equals 2, let C equal B plus 1. So these can be any expression that makes use of the locals that have already been defined. If you've ever used another list like Scheme or something like that, let is actually that this isn't guaranteed to work in Scheme. They're considered to be parallel bindings. That's not true in Clojure. They are really literally happening in order, so you can rely on that. And then you can evaluate an expression that actually has that set of bindings known. And then now I'm outside the let expression, and that A doesn't have any meaning. It only meant something inside that lexical expression. All right, so you've now seen a lot of Clojure, basic Clojure. So now we're moving into a little bit of abstraction. So we have these core data structures, these core collections, vectors, lists, maps, things like that. Something like Common Lisp has a fantastic library for working with lists. And the key insight here behind sequences is that it's a shame that has to be locked into an actual concrete collection just in lists. It would be better if we had sort of a logical list abstraction that we could use on any collection that was able to present itself as if it was a list. And so all of the core Clojure collections have the ability to sort of show themselves as if they were a sequence. And that means that you can use lists, vectors, sequences, or list vectors, sets, and maps all with sequence expressions. And so there are a bunch of collections, and you can define your own. There's a bunch of different ways to make your own kinds of sequences. And a sequence is just something that you can ask for the first element, and you can ask for a sequence that's the rest of the elements. That's the whole API, basically. And so you can see how you can apply that to lots of stuff. So there are functions in Clojure to give you back, the lines in a file as a sequence, or the files in a directory as a sequence, or the rows in a JDBC query as a sequence, or anything else you can come up with. There's any number of things you can view through this lens of a logical list. And you can also just create sequences themselves. Range is often used. It starts from 0 by default. There's some other rarities that do other things. But it's used for examples a lot because it's really easy to gin up a sequence. Map is one of the most common. Map filter reduced to 3 of the most common sequence functions. Map applies a function to each element in a sequence. Here I'm actually passing in a vector, but that vector will automatically present a sequence view of itself. Whoop. Sorry, I just lost my screen here with a little wire or something. And so if you do that, you'll see that this increments 1, 2, and 3 and returns to you 2, 3, 4. You might, if you're sharp-eyed, you might notice that it returns to you something that's in parentheses, not in not a vector, and that's because map is a sequence operation, so it implicitly converts its argument to a sequence, and then will return you something that is also a sequence. So it's been converted into some kind of a list-like object. There are ways to get back to vectors and stay in vectors. There's a bunch of different stuff there. I'm not going to talk about all the details of all that. We could also say filter, which says basically filter down to just the things that satisfy some predicate. So odd is obviously a predicate that will filter for odds. And then you can kind of stack all these things together and say, I've got a range 10. I'm going to filter it to odds. I'm going to map over it and increase by 1, and then reduce by summation, basically, and get back to a number. And a lot of times people will say, oh, well, I find it really difficult to read this Clojure code, that you have to kind of read it inside out. I just evaluated it from the inside to the out. And Clojures are not weird. They also find that hard to read. So there are some very common macros that are used in Clojure to basically invert the way that looks. And so this is something called the thread last macro. There's also a thread first macro, which is used for collection operations usually. All of the sequence functions take the sequence as the last argument. So you notice that this is the last argument passed to filter. This is the last argument passed to map. That's why we got this big pile up of parens at the end, right? What this does is says, evaluate the first expression, take the result and drop it in as the last. That's where the last part comes in, as the last expression and as the last argument to the next expression. And then evaluate that filter and take the result and drop it in here at the end. And then take that result and drop it in here at the end. And so I've used those commas just to mark where things are happening, but remember, commas are white space. They're totally ignorable. So what we've done here is just change this thing that you had to read inside out to something that you can read, top to bottom or left to right, something like that. And this is very common to see in Clojure code. You'll see stuff like this all the time. It just helps out with making things a little tighter, more readable. Sequences also can be infinite. So cycle here is actually a cycle that takes a sequence of elements, in this case 1 and 2, and then repeats them forever. So this is actually an infinite sequence of 1, 2, 1, 2, 1, 2. I'm not going to print it because printing infinite sequences takes a long time, but you can take some off the top, and and I can take more if I want. There's an infinite number of them. I can take as many as I want. Repeat is a similar thing. It repeats a single element infinitely. And then an interesting thing you could do is to take map and actually map an operation over not just one sequence, but actually 3 sequences that get walked, or any number of sequences that get walked in parallel. So this is an infinite sequence of 1, 2, 1, 2, 1, 2, an infinite sequence of hundreds, and then a finite vector of 987,654. And map will just stop when it comes to the end of the first vector. If you happen to pass it all infinite sequences, it will just return you an infinite sequence. That's totally fine. And so, as you may guess, it's not actually building an infinite sequence in memory. It's more of a sequence that has reified part of itself and knows how to do the next one, right? So in general, as you need more, it will go make more. Another common idiom is to construct a map by zipping together the keys and the values. In this case, the keys here are keyword names. The values are, say you're making a map of scores for a game or something like that. You want to start them all with 0. And you can kind of zip those 2 sequences together and get a map. But I've zipped together a finite and an infinite sequence when I did that. So that's kind of a common idiom. All right, so that's the basics of sequences. Where we start to get into stuff that may look more like what you're doing on a day-to-day basis is your programming. Is talking about maps, using maps for information. So in the case where in Java or something like that, you would create a person class. Instead, in Clojure, you would just make a map with well-known field names. And so field names are virtually always created with keywords in Clojure. I mentioned that they are immutable, that they value to themselves. They're interned, so they're very efficient. You can make 1,000 different of these person objects. They're all going to use the exact same first keyword instance in memory. So that's efficient. They compare very fast because they are literally that same identical object. So the JVM can make use of that and do real fast comparison. We might have, in this case, 3 fields that are first, last, and Twitter ID. So if we get that, we got a map then. And there are ways to pull out, individual fields. You can use the get function to get the first field from person. And then if you look back at this map, you can say, well, a person is a map, and a map is just a mapping from field to value. So that's actually a function. So it turns out you can actually literally use a map as a function. So here we're actually putting a map in the function position, and we can evaluate it, say, what is the thing that's mapped to the key in this person? So that works fine. That's not something we actually do a lot of in Clojure, because if this happened to be nil, for example, you'd get an null pointer exception or illegal argument exception. So that's not good. So typically you only do this in cases where you know for sure the map that you have in hand is not nil. So if it's like a literal map, something like that. What's far more common, though, is to actually invoke a keyword. So keywords actually are also functions. You give them a map, and they look themselves up as a key in it. And that sounds weird when you first hear it. It turns out to be one of the most astonishingly useful things that we have in Clojure, being able to use field names as functions, basically. And it's totally fine if this is, an empty map, we'll just get back nil, or if it's nil, we'll get back nil. It's very tolerant of all those kinds of things. It's totally fine. So let's define a few collection of people here. So I've got a vector of maps. Like I said, everything is heterogeneous, everything nests. You could put maps in vectors in maps, and yada, yada, yada. That's all fine. And then we could use map. Map, remember, applies a function to the elements of a collection. And so we can actually apply a field name to a set of people and get back a bunch of results. And so this is, if you translated this back into Java, this is like saying, I have an array list of person objects, and I'm going to apply the, get Twitter ID function across all of those objects. You can do some of that stuff in Java now with the function APIs. That's not something you used to be able to do, but this is just like a totally normal thing in Clojure. And this is where you start to have this very generic way data interface, where you have a generic way to always get a field out of any sort of entity like this. Any questions at this point? Let's see what time check is it. 7:30. All right. So I think I'm going to skip through a little bit of this. Yeah, there's a question of, is Clojure dynamically typed? Yes, Clojure is dynamically typed. Like if we went back and looked at one of those functions that we had before, capitalize, I didn't say what type this was. It's possible that if you wrote a function generically enough, that you could have a function that actually worked on multiple types, and that would be totally fine. But I would say in general, a lot of functions like this, you do kind of know what the type is going to be. And there are ways when you're using Java interop to basically type hint and tell the compiler, you don't need to use reflection. I'll help you figure it out a little bit what you've got there. There is some type reference inside the compiler to do that automatically. I'm trying to think if there's any happening here. Yeah, I don't. think you're getting any effect of that in this example, but there are ways to create things like that. Can you add gradual typing like in TypeScript that the compiler can enforce? So we haven't talked about ClojureScript at all, but Clojure has a dialect, which I think literally everything you've seen to this point is exactly the same in ClojureScript. And ClojureScript does have a little bit more support for type inference and type inning. It's a little bit more involved than what you have in Clojure. In both cases, though, it's not really about enforcement. And so there are some things out there, some statically typed or gradually typed add-ons to Clojure that do various parts of that, but that's not really in the core. It's not going to be in the core. It's not the goal of Clojure to do that. So you're not going to get that. But the surprising thing is, in general, you often don't need it. So if an if, does the then expiration else which have to be the same type? No. So if you want to write an if expression that says defin foo x if odd, then return x, otherwise return ABC. Right? So you could say foo 5 gives you back 5, that's fine. But if you give it an even number, it actually gives you back a string. That's probably pretty weird. There's, for all of the obvious reasons, calling that function means you have to understand that you might get back something of a different type. So this kind of a thing is not something that you actually see very often. But it doesn't care. So it's totally fine. It's actually the byte code that it's generating under the hood. It's using Java object, like the type object, for all of the inputs and the outputs in general. All right, where were we? So structuring. I'm actually going to skip over to structuring. Structuring is a really nice way to, it's basically a shortcut to allow you to specify, to give names, local bindings, to parts of a compound structure. So in a very concise way. So if you get past a vector V, you might say, I want to get out the first thing and call it A, and the second thing and call it B, and the third thing and call it C. So destructuring lets you do something like this instead and say, that V has this structure with elements A, B, and C, and they get pulled out and named A, B, and C. So, and there's some other examples with you can do with maps and lots of additional stuff, which I'm not going to cover, but it's basically a very concise way of creating a bunch of local bindings based on the structure of the value that you get passed. So that's the shortcut for destructuring. Namespaces, we haven't really talked too much about namespaces. I'm actually in the user namespace by default, and that's why you'll see users showing up on things that I make here. But there are other namespaces in Clojure. So like Clojure.string has a bunch of string functions in it. I can call those to do things like take a sequence and combine them with some intermediate character, make a string. There's lots of other things. There's a lot of discoverability built into Clojure. So you could say, what are all the other functions that are in string? So you might see, oh, there's a capitalize. I did need to write that before. There actually is one already. And you can do that either on the fully qualified namespace or actually on the alias that I created up here for it. You might say, well, I wonder how that's implemented. Oh, okay. Well, we can actually go look at that. So if you're pulling those functions out of some namespace that's on the file system, we can actually get to the source for it and go look at how that was implemented. And most Clojurists report that they spend the first 6 months of writing Clojure looking up how different things are implemented. And it's an important part of the learning process as you write Clojure. You could say, I know there's something like join, but I don't remember exactly what it's called. Go find me some things that have join in the name. So it found Clojure string join, but also found, oh, there's a Clojure set join. I wonder what that is. So it actually does some relational algebra stuff. And then there's Clojure test has something to combine fixtures. I wonder what all those things are. If you want to pop up some Java doc, you can do that. I actually popped up in my other window, but popped up some Java doc there. I happen to be using Java 11. It actually pulled up the Java 11 Java doc. It's actually sensitive to what version you're on to some degree. So that's kind of cool. I did want to talk about Java interop because I presume that most of you are doing Java. Import is kind of like the import statements in their Java file, allows you to basically import a class that's in a package, and you can actually import other things like other classes that might be in that same package. And the only benefit of that is that it allows you to basically reference that class just by its short name at that point in your current namespace. So here we're just calling java.io.file. This is actually the constructor notation. So if we take the class name and put a dot at the end, that says construct a new file and then invoke its constructor and pass it whatever arguments you need to. I can actually put that in talk file. If you look at talk file, you'll see it's a Java.io file. I can then invoke methods on it. You might want to call .exists on it or convert it to a Java.io path. Things like that. There's a handy function built into Clojure called Slurp that actually takes a file and reads it as characters and gives you back that as a string. So this talk file is actually this file that I'm in right now. So if we look at talk here, it's actually this file. That's the whole file I'm in as a string. I might want to then take that and say, like, take that talk, map over it, and convert every character to lowercase. So here I'm actually invoking a static method, which uses class/method name, and then filtering it to. So this is kind of an interesting use. We mentioned before that maps could be used as functions. Sets can also be used as functions, and they check whether the element you pass it, or the object you pass it, is an element of the set. So this says just filter to all of the letters that are one of the vowels, and then give me a frequency map on that, which is something built into Clojure core. So you can see that in this file that I'm in right now, I had 336 E's and 251 A's and whatever. So it's just kind of an example of sort of mixing Java interop and sequence functions and using the thread macro and that kind of stuff. So if you write Java interop type code, you do stuff. This is a pretty representative example. There's a function called class that lets you take an object and will tell you what class it is. So unsurprisingly, that's a Java line string. You can also use just the class name by itself is the class object. So if I just look at this is actually it's a little hard to see because the toString of a class object is just the name of the class here, but that's actually the class object, and I could call get declared methods on it, which gives me back actually an array of method objects, and then I can run bang is a variant of reduce basically that says run a function with side effects over some seekable thing. And so here I'm just going to print the toString of all of the methods I got back in the string object. It should look familiar. Oops, I just clicked off of where I was. There's also a handy function called bean. Bean actually uses the Java bean semantics and will give you back, will act as if it was a Clojure map whose fields are all based on the getters in the bean. So I'm sure are familiar with the Java util date object. It actually has a built-in representation in Clojure. But trust me, that's a Java date object. And if we call bean on that, it actually goes and reads the get day, get date, get time, get month, get seconds, get year, get class, whatever, and gives you back a bean representation of it. There are some caveats with this, and it's not something I typically use in real code, but it's It's super handy when you're at the Repple and just want to get an idea of what you're looking at. So it can be useful at times. Another important thing is that every Clojure function is also an instance of runnable and callable. So thread, for example, Java lang thread is something that takes a function, it takes a runnable. So I can just drop this function in that says println hi and then the name of the current thread. So I'm using static method there, instance method here, doing some interop. So that basically created the thread, but I haven't started it yet. So I started it. So that just spun up a Java thread and printed out which thread it was. If I do that, I can't do it again because I already did it. But I can create another one. Another thing to mention here is that this due to macro is kind of useful to take a Java object and then invoke a bunch of methods on it. And it threads, kind of like thread first, actually. It takes this object and drops it in as the first argument to a Java method call. And then at the end, it returns you that object. So if you've got a mutable Java object of some kind, you can construct it and then call a bunch of methods on it, and it will return to you the list. So this returns a list, a Java list with, it's got 3 elements in it. And that's actually printing using, it's using the Clojure printer there to help it out a little bit. And then Java list compared to Clojure vectors, true, that's fine. Clojure vectors and lists actually are, actually implement Java util list, and the maps implement Java util map, and the sets implement Java util set. So you can have a Clojure API and actually return Clojure collections directly out of it, and the Java on the other side of it, as long as they only care about the interface support, can use that just fine. So it makes interop pretty easy from the other side. There's some handy, this is just showing that if we take a Clojure vector, take its class, which is actually a persistent vector, and then look at the ancestors of the class, you'll see that Clojure collections implement a whole bunch of interfaces. Clojure ones you can mostly, but you'll see it's because vectors are actually also invocable. You can treat them as a mapping from index to the element at the index. So Clojure vectors are runnable, they're iterable, they're lists, they're serializable, they're Java util collections, callable, they're random access. So they implement all sorts of stuff, right? And comparable. So you get a lot of that stuff for free. It's all good things that get done there. Mentioning Clojure exception handling, you should understand exactly what's happening here. Running a body, it throws an exception, we catch some exception type. You can have multiple catch blocks, just like in Java. They'll be checked from top to bottom. We can name the exception that we just caught and then use it in an expression after that point. You can also do a finally block. So after that, that's just fine. So you'll see the hi came out there at the end. I have a longer example of integrating Clojure into a Java code base. I think I'm going to skip that, but there is actually a Clojure Java API that allows you to, from Java, look up vars, invoke them, use the reader with read, and do a few of those basic things. And that's enough to hook you into using Clojure, basically. So it's not too bad to sort of, my preferred way of doing integrating some Clojure into a Java code base is to write a Java interface for all of the things that I care about. Write Java doc and figure all that stuff out, and then basically have a little factory method that instantiates a Clojure object that reifies the Java interface. And we haven't talked about reify, but there's actually a reify interface that you can use to to do whatever. So you can basically create anonymous objects that way, or there's a couple other ways to make Clojure things that implement Java interfaces There's several ways to do that. So at that point, the caller doesn't care. They're just using Java interfaces. They have all the docs they need, and it's pretty easy to hook into that way. I do want to talk about concurrency and state a little bit. Where we are here. I'm going to try to end within the next 15 minutes. So concurrency and state. Future is a useful tool to throw some work into the background, throws into a background thread pool. So here I've got a function that says for 1 to 10, from I 1 to 10, println a dot and then wait 2 seconds. So I can throw that on the background. And so off in the background there, it's doing stuff. I can, do some more things. It's still printing. It's in a different thread. There are ways to, so that actually returned a future object, which you saw up here. I didn't capture it, but if you capture it, you can actually block and wait for it to return whatever result comes out of that thing. So you can use the normal future API. We can define, we might need to maintain some state. So say you've got multiple threads that actually want to hold on to the same, point to the same stateful thing and communicate about that. You can do that with Atom. This is really similar to Java Util atomic reference. It's based on top of something like that. But here we've created an Atom that is a vector. Put that in a var. So vars are global, so all threads can see this. I'm not using more than one thread right now, but if I were, they could all see it. The @ sign is a helpful little bit of syntax sugar. It's actually read by the reader and turned directly into this. These two are identical in terms of what they do. And all it says is dereference the atom and tell me the current value. So the value could be changing. Other threads could be changing that value as they do work. But that's fine. We'll see whatever. It's a safe read. So it's maintaining all the, you don't have to worry about locking and all that kind of stuff. It's the right thing is happening there. Swap bang is a function we can use to modify the value in the atom. And the key thing here is it's not passing in a new value to use. It's not passing in a value, a new vector with the value 100 in it. It's instead going to pass a function that says, how do I modify the current value? And when I apply the function, I'll get back the new value. And that means that we can, you might have multiple threads that are doing this at the same time, and they're going to interleave. So, but they're going to interleave atomically. So you're never going to get any kind of mismatch between those things. And this swap bang is very fast. So it says basically swap the scores atom by conjoining into it 100. So add 100 into this vector. And so when we do that, it actually returns the new value. Do it a few times if you wanted, and then dereference it and look at that. It's totally fine. The downside of atoms, and atoms really are the sort of 90% case, or maybe 99% case for what Clojurists typically use for state in their application. It was not obvious when Clojure first came out that would be the case, but over time that has turned out to be between immutable data, immutable collections, and atoms that actually takes care of the vast majority of state and the vast majority of programs, which is surprising. I don't think that was obvious when Clojure first was created. But if you do need coordinated change to multiple stateful things, you can do that with refs. And this is where we start to break into the Clojure software transactional memory system. Ref, kind of like an atom, is just wrapped around a value. So you might create a savings account and a checking account that are 100 and 0 at the beginning. We can define this function transfer that says from a ref to a ref, transfer this amount. DoSync is what defines a transaction boundary. So inside the DoSync, we have a body set of expressions, and those expressions are either going to succeed or fail, not halfway. So this says alter the from reference by subtracting the amount, alter the to reference by adding the amount. And we're guaranteed by the software transactional memory that either neither of those is going to happen and the transaction will fail. There is a retry system which will retry it a certain number of times if there happens to be a conflict. In general, getting conflicts out of the STM is exceedingly rare. I have never seen it in actual code actually happen. I think it retries up to 100 times or whatever, but I've found it to be difficult to even get it to retry once. But anyways, so that's the scope of that transaction. And we can then say transfer some savings checking. Here I'm dumping a vector, which is dereferenced savings and checking, so we can see what happened. So we can do that again, and I'm just doing this in one thread, but you could do this in multiple threads. Everything would be fine. We might want to reset this, make our savings account much bigger. Here I'm going to say I'm going to spin up 1,000 jobs, push them onto a background. It's actually a pool of threads, so it's not going to be 1,000 threads, but it will be a bunch of threads. And I can, do this it was already done, so it was pretty fast. But they were all contending for that while I was doing it. So, sorry. So that's the basics of state and concurrency. There's lots much more complicated things you can do. I'm skimming over a lot of that. I'm just hitting the tip of the iceberg here. But I mentioned before that we break reading or evaluation into reading and break it into a reading and evaluation. And I wanted to revisit what's happening over here in this REPL, because it's kind of important to understanding the model of Clojure. The REPL is not some complicated program. It's just a function, and that function is literally doing printing, reading, and eval. And these are all functions that are available to you as well. So here I'm using read string. There's actually a read method, which is reading from a stream of characters, but read string is the same thing. It's just a little more convenient to demo. So when I have something like this, I'm reading this string, left paren plus space 1 space 2 left right paren. That's being turned by the reader into a list containing the plus symbol, 1 and a 2. And then eval is actually evaluating that. And that's exactly what's happening over here. And we could do that ourselves. We can say, read the string into a collection, evaluate that into the number 3, print that 3 back to the output. And the REPL over here is really nothing more than a composition of these 3 things in a loop. And I could, I don't have a handy link to it, but I could just show you the actual REPL that's running over here. It is literally doing these things in a loop. There's a lot of other little details in between it to handle a bunch of error handling, a bunch of other things, but that's really it. So it's important to understand that there is nothing magical here. When you read a Clojure file and evaluate it, all it does is starts at the top of the file. It reads the first expression, evaluates it, and doesn't need to print when it's doing that. And then it goes on to the next expression and it keeps going. Reads, evaluates, reads, evaluates, reads, evaluates. So there's really no difference here in what I'm doing or how Clojure is evaluated. I did want to mention macros before we get to the end here, just because that's something that you've undoubtedly heard about with Lisps, and it's an important tool in our toolbox. So I do want to mention that. There is no unless function in Clojure, but say we wanted some unless function that said, unless this is true, unless this is false, sorry, it's the flipped case. Unless this is false, do some body of expressions, print one, def mode, print one. So if I evaluate that, there is no unless built into the library. But I can write a macro to create that. And it's important that this can't be a function. We can't write a function that says, unless f, so we don't collide here. And the ampersand here, I don't think we saw this before, but that's just creating a variadic function. So body is a sequence of things at the end. So you could say if not condition, then evaluate the body, something like that. So there's 2 things here actually that are that that are a little difficult to write. And the first is that we don't want to evaluate is that when you invoke a function, it evaluates. Remember, the evaluation model is that when you have a list, you evaluate each argument and then invoke the first one. But we don't want to print these things. We don't want to evaluate these. We want to defer that evaluation. And that's something that we need. And if we need to boil that down into an if somehow, right? Or a when, which is like a one-armed if. So that's something that we can't do with the function. And also this thing with the body of expressions, we can't put body in there. Body is actually a collection of things to evaluate. And so it's a little more, you could do it with eval, but it wouldn't be too pretty. So for all those things, we really want to step into the middle here. And the key thing with macros is that they get activated in between the read phase and that eval phase. So we're going to read this thing, and then before we eval, macros are basically a function from code to code. So we read the code, and then a macro, Clojure will check and see, is the first element in this list a macro? And if so, it will invoke the macro and give it this as a data structure, right? It's already been read, so it's already in data. So a macro is just a function that takes a data structure representing code and returns a data structure representing code. And the compiler then replaces what it had with whatever the macro returns. So it's giving you this hook into, it's basically a user-side compiler hook that you can use. And if it happens to return something that also has a macro in it, that'll get unrolled too. So it'll keep unrolling and unrolling until it gets to a function that it can invoke, and then it'll invoke that. So this is one way to write this macro. You can take the condition of the body. This is a special kind of quoting called backtick, which I'm not going to get into the details of all this stuff, but it basically is sort of, you can think of it as sort of a template for the code you want to emit. And you're taking these things that are being passed into the unless and dropping them into the template. So once we create that, then we can go back here and actually evaluate this. And you'll see that the system property has not been set, so it prints dev mode. But then I can set that, that's fine, and then try it again. You'll see that it did not print dev mode this time, so it works. And it turns out that unless is actually exactly the same as a function that a macro that already exists in Clojure called when not. We could look at the source for that. You'll see it's a different implementation here. It's in some ways a little bit more straightforward. It's taking a test and a body, and it's actually literally constructing a list. List is a function that creates a list. It takes the symbol if, the test value, a nil, that's the first part of the if, the then part of the if, which we don't care about, and then the else part of the if, which is cons, which says take this sequence of expressions, construct a new list that has do at the beginning, and this is the remainder of the list, and then include that in the list. And there's actually a helpful tool called macro expand. You can say macro expand and then just copy the code I have in here. And so you can expand that and say, what does that look like when I expand it? And you'll see that it looks like, so we want it to actually, oops, dang it. I keep clicking on the right gutter and it moves me. I'm going to use a function called pprint to format this a little bit better. So you'll see that it says if not system get property, then do print one dev mode print one. So it basically, when we call this code up here, it invokes the macro returns this code, and then the compiler walks on working with that. So there's a question, how do you eval the function doc only? Eval the function doc only. Sorry, but I don't know exactly what that means. Yes, you can have self-modifying code. So it's not modifying, going back and modifying the source code that you have, but we just did modify code. So could you reevaluate the thing that you are currently expanding? Yes, but generally, yes, with some caveats. And generally, you're not going to want to do that. So that's not a common thing that you would do with Clojure. Function I print as doc. Just doc. Yeah, so if you use the doc function, it would do that. So it just prints the doc string and a few other useful things after that. If that makes sense. So I obviously can't cover everything about a language or its ecosystem in an hour or hour and a half or whatever. But web stuff, yes, there's lots of web stuff. So there are libraries to do routing and HTML generation and CSS and whatever you want. And really, most libraries in Clojure take the tack of take the domain that I care about, how do I represent it as Clojure data structures, then just use Clojure. We already have all these this big library of things that we can use to manipulate Clojure data, and then either could turn that into logic or turn it into emit it to something else. If you want to do front end stuff, so ClojureScript is a dialect of Clojure, which is 99% of the stuff I just showed you is exactly the same in ClojureScript, with the difference that ClojureScript uses the Google Clojure compiler to transpile to JavaScript, and you can then put that into your web page or whatever and use that. And the cool thing is there's actually a I'm in a .clj file. ClojureScript uses a .cljs, and then there is also another extension you can use called .cljc, and C stands for common. You can use that for code that you want to use in both Clojure and ClojureScript. And then there is a syntax called reader conditionals that lets you sort of special case anything that happens to be different between them. And that means you can basically write your domain functions and your domain models and your core logic. You might have validation logic or something like that. You can use literally the identical same file to do that logic, both in ClojureScript that gets transpiled in JavaScript and runs at the front end, and you can do this in the back end in your back end application. And so that is pretty awesome. If you want databases, there is access to Java or to JDBC, or there are bindings to literally every database out there in Clojure. You will not want for anything there. UIs, there are really good Clojure bindings for Swing and JavaFX. There are some real applications out there written in JavaFX that people use for things. There's a fairly popular game editor, actually, that's written in ClojureScript and written in Clojure and JavaFX. There are a lot of different tools these days for machine learning. There's some that are written in Clojure. There's some that wrap Java APIs. There are some newer things that actually basically can hook you directly into GPU level stuff. If you're interested in doing data science and you want to access to, say, like Python or NumPy or something like that, there's actually a fantastic Clojure Python integration that's been seeing a ton of work in the last couple of years, and it's gotten really good. And you saw those requires that I did earlier. There's ways to actually just like literally require NumPy, and then you could start using it directly from your Clojure API. And it's a fantastic way to front all of that stuff that is already built and people are using inside Python. You can wrap that stuff in Clojure now and do the rest of your application in Clojure if you want, and use that directly. And that's gotten really good and really interesting in the last year, especially. There's actually an interpreter for Clojure, or a dialect of Clojure, called Psi, the small Clojure interpreter. That's actually written in Bash, so you can run that directly. And there's also a thing called Babashka, which is basically it's basically a Clojure interpreter or a Clojure compiled with Graal, creates a native image, and you can use that for command line scripting kinds of things. That has gotten really good over the last year or two. So you can use Clojure all over the place if you want to, once you get comfy with this stuff. And all the basic stuff that I just showed, all that stuff works the same in all of those dialects. There are definitely differences once you get into, domainy type things. The hook for NumPy, there's a thing called, it's called Clojure-Python, I think. I'm blanking on exactly the name of it now. It's called CLJ, or libpython CLJ is the name of it. And then you can go from there into NumPy and stuff like that. Chris Nurnberger is the guy who's been working on that stuff, and he's been doing all sorts of great stuff with it. You can look into like NuPlot or ggplot or whatever the plotting libraries are, and people are using it for that now. So it's pretty cool. So the why for me is really the list that I had at the beginning, which I've repeated again here. For me, all of these things make it just a total win over Java. Obviously, Clojure is not as frequently used, as commonly used as, or as popular as Java. It will never be as popular as Java. I'm totally fine with that. But there are hundreds of companies out there using Clojure. The biggest bank in Brazil, Nubank, has 500 or 600 Clojure developers, and they're using Clojure for everything. And I don't know if anybody's seen Roam Research has been a kind of a popular note-taking app that's been getting a lot of traction on Twitter lately, and that's all a Clojure-based project. It's great for very rapidly prototyping things and then actually moving it in, transitioning that very seamlessly into something that could be a real production app. So it is used out there. There's tens of thousands of Clojure developers and hundreds of companies using it. There are jobs. The jobs, this is something where there are jobs and there are a lot of developers, but they are not sort of geographically or experience level distributed at the same level. So it can be a little more challenging to get a Clojure job if you don't want to work remote, you don't happen to be co-located with some company that's doing it, or you happen to be a real new Clojure developer. There are companies that hire, I know several companies that have Clojure companies that actually don't even try to hire Clojure developers. They just try to hire good developers and then teach them Clojure. They generally find that they can be doing useful work within a month and pretty good within 6 months. And so they found it's really easy to teach Clojure. I just taught you the core of it in the last hour. That's enough to be dangerous. So I think that is all I have. This repo, this file, and this repo is actually linked it up here. It's at github.com/puredanger/clj-intro, and I'll give that to Bruce as well for afterward. It has this file, and there's actually another file called cards in here, which has a couple of card examples that I didn't get to. Well, that's in there too. There's a question about testing frameworks. Clojure actually has a test framework built into it. So there's something called Clojure.test. You can do things like assertions, things like that. You can define tests, stuff is equals 1. So there I just wrote test, and then I could say run tests. So it just ran all my tests. So that's what Clojure.test tests look like. If you're just getting started, I would recommend using Clojure.test. That's probably the most common thing that people do. There's another great library called Expectations that is a little bit closer to sort of behavior-driven development type style stuff. And then a lot of Clojures actually use a library called TestCheck, which is a generative testing library, which lets you basically generate a vast number of inputs, apply them to some set of assertions, and then validate that those are true. It's property-based testing or generative testing, or that's what that's called. That's the test.check library. I generally use both for different things. As you can see, I did a lot of testing here in the REPL. And so there are a lot of Clojure functions that I look at and I think I don't need to write a test for this. It's really, I'm just relying that the Clojure core functions do what they say they're supposed to do. And I don't find that writing a test for that is generally very useful. But as soon as you get some real logic or some domain stuff in there, you want to write some tests. Can Clojure be compiled ahead of time? Yes. So I'm not showing it here, but I mentioned before that you can that when you're evaluating these things, it's actually creating classes and loading them dynamically into a class loader. You can also say write those classes out to disk and build a jar file for that. So there's actually a compile function, which is how you do that. So you can just call compile and tell it to compile thing. It actually will transitively compile all the things that namespace depends on. There are some things to know about that. It can get complicated at times, but there are build systems that work with all those things. Clojure fully embraces the Maven ecosystem. All of the Clojure build tools out there work on top of the Maven ecosystem for as far as deployment or whatever. So the equivalent of something like pom.xml in this project, I have a deps.eden file that defines my source code path and my dependencies. So this is a full equivalent to pom.xml, so it's much more succinct. There are other things that you might put into, a build type definition like library name and deployment and all sorts of different stuff. And there are other build systems, and I'm actually working on a new project to fill this hole for deps-based projects like this right now. So that will be out hopefully soon. Yeah, this is using Maven. So we'll out there and do things. Most Clojure build systems deploy libraries as source code, so as CLJ files, and don't AOT compile. Generally, we recommend that AOT compilation is something you do at the app level, because that's the point where you know which Java version you're on, which Clojure version you're on. You don't want to make those decisions early in a library. You want to let the application make those decisions late. So that's the big reason for that. All right, well, seems like the questions have slowed down and I've kept you for a long while, so I'm going to end here. Thanks everybody for coming. If you have any questions, feel free to, you can find me on Twitter at Pure Danger, or there is a great Slack channel called the Clojurian Slack channel. That's clojurians.net, I think is the link for it. If you do that, you can get into the Clojurian Slack channel. There are always people on there willing to help. It is an extremely beginner-friendly community. Feel free to ask questions on the Clojurian Slack, and I'm on there most of the time as well. So happy to help. All right, thanks everyone.
All right, thank you very much, Alex. And we hope to see everybody here next month. Thank you very much.